So, um, so Matthew Colbrook is an associate professor in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge, working at the interface of applied mathematics and data science with a focus on spectral computation, Koopman operators, and the foundation of machine learning. His research develops rigorous and practical algorithms for extracting spectral information from high dimensional and infinite dimensional systems with applications to dynamical systems, inverse problems, and scientific computing. He had received several distinctions, including the 2026 SIAM Early Career Prize in Data Science for his work on Koopman operators, and the SIAM Richard C. D. Prima Prize, and the Vasu R. Popov Prize for contribution to approximation theory and spectral computation. His forthcoming book, to appear in summer 2026, develops a unified and computationally grounded approach to spectral computations in infinite dimensions with Koopman operator methods playing a central role. So Matt, take it away. And you said that you want to get questions if people have questions in the middle of your talk,
Yeah,
just
that'd be great.
to pop in and ask a question. So, all right, take it away.
Thank you. Yeah, thank you for the invitation. It's a pleasure to be here. So I'm going to talk about trustworthy Koopmanism with a focus on spectra forecasting and dictionary learning. But the unifying theme throughout this talk is managing non-closure in finite dimensional approximations. Okay, so we all know that the Koopman operator is this infinite dimensional beast, and that we somehow have to truncate to a finite dimensional subspace. And I'm going to look at sort of what happens when you do that and what you can lose and how you control that. Okay, so I'll put the slides up on my website afterwards. You can find previous talks and papers on my website here, either through the link or the QR code. Okay, so this slide is a bit redundant probably for this community, but let me just set up the notation. So throughout this talk, I'm going to be dealing with discrete time dynamical systems. So I have a state space, capital X, a state, small x, and then the dynamics will be governed by a continuous map. Okay, it's map F. So the state of time n+1 is f at the state of time n. And then we all know the story that along come Koopman and von Neumann in these two very nice papers. And they look at what happens when you study not just the state and how that sort of hops around the state space in a nonlinear fashion, but observables of the state. Okay, so these are functions from capital X to the complex plane, so not just real valued, but complex valued. And for the first part of this talk, I'm going to be dealing with observables that live inside an L2 space. Okay, so you always have to be careful about which space your observables live in. So if you get lost at any point, just think of the L2 case. So this is L2 with respect to some positive, not necessarily finite measure. And then the Koopman operator acts on an observable by composition with F. Okay, so you're observing this observable one time step forward. And this is a linear operator. So this state space, it might not even be a vector space, right? So it might not even make sense to talk about a linear function here, but you always nevertheless get a linear operator down here. And then the sort of framework that, or the setting rather, that people are looking at the moment over the last 10, 15 years is what happens when you don't know the function f, or maybe it's too complicated to study directly, and instead you're given a set of snapshot data. So snapshot data is just the fancy name for samples of this function f. So we have a finite number of samples, x in blue, y in green, where y is f of x. And the first sort of question that I want to consider is how do we use this snapshot data to compute spectral properties of the Koopman operator? Okay, so a question you might have from the get-go is why would you want to get the spectral properties of the Koopman operator? There are many reasons, many sort of nice properties of the dynamical system that are encoded in this spectral information, but I just want to give one simple example. So suppose you get something called a pseudo-eigenfunction, or you can compute it. So this is a g, an observable, and a scalar lambda, where the norm of kg minus lambda g is small. Okay, so it's bounded by some tolerance epsilon. Then if you take this formula, okay, so for marching forward n time steps, you're applying the Koopman operator n times, you get an approximate power of this approximate eigenvalue lambda appearing here, and then something that's order n epsilon. So I've hidden in the order here some things to do with the norm of the Koopman operator and the eigenvalue, but that doesn't really matter for the sake of this talk. And the big O, the error here is measured in whatever norm you're working in. Okay, so you get these approximate coherent features, and you can do this even for complicated um, chaotic flows on things like fractals, like the Lorentz attractor here. So here I'm actually showing smoothed approximations of generalized eigenfunctions over the continuous spectrum. So you'll probably seen the left figure here in, let me find my mouse, in some papers as well. For example, Igor and Dmitry also approximate this generalized eigenfunction. But what I'm showing you in the video is how these evolve over time. So this is real time. Okay, so even though you've got a chaotic system, you get these coherent features that are sort of giving you some sort of pattern that is pretty stable as long as epsilon is small. Okay, so we can actually um, look at a spectral set that captures these coherent features. This is called the approximate point pseudo spectrum, and this is the set that I'm going to be trying to approximate throughout the first or the majority of this talk, rather. So this is all, for a given epsilon, this is all z in the complex plane, such that there exists an observable of norm 1, where kg minus zg, the norm of this is at most epsilon. So this is giving us sort of, in the spectral region, where can we see those coherent features? And then whenever I'm sort of introducing Koopman to people who haven't seen it before, I always say it trades a nonlinear finite dimensional sort of setting to a linear infinite dimensional spectral problem. Okay, so hopefully this kind of idea is familiar to people. If not, by the way, just shout out if people have questions or if something's not clear. It's much better if I stop and explain something. Okay, so you have this set. You might also want to use this, for example, to forecast. And this is one application that I'm going to talk about later from a paper with Igor for sea ice. So suppose, for example, that you have some pairs of observables and lambdas. So these are your approximate eigenfunctions and eigenvalues that approximate that satisfy this equation here. Suppose also you're interested in an observable h, and you can get an approximate expansion. Okay, and these coefficients are called Koopman modes. So if you took a vector of these guys, you then get a vector of the Koopman modes, and that's what people typically plot in fluid papers and things like that. Well, if you have this expansion, you get a forecast, right? A prediction where you're just replacing the how each of these GJs evolve through time by powers of the associated approximate eigenvalue, and then you get this error term as well. So the intuition is really sort of a nonlinear separation of variables through a linear operator. And this is sort of, the power of Koopman is that we can turn something um, complicated, nonlinear, even chaotic into a linear, infinite dimensional problem. And somehow controlling the truncation error from infinite dimensions to finite dimensions is easier to understand than dealing with the original nonlinearity. One thing I should say is that you don't always get all of the information about the dynamical system from the Koopman operator. That depends fundamentally on the space of observables that you look at. So for example, if we go back to the slide here, if you're in the L2 case and you're looking at ergodic systems, you only capture up to conjugacy all of the information if you have discrete spectrum. So it's a classical result, but I'm not really going to go into details in that sort of stuff in this talk. Okay, so we want to get the spectra, and probably most of you have seen this slide before. If not, I'll go through it. If you have, then it's good to be reminded. And one should always be careful, okay, when you're in infinite dimensions. So we've got this infinite dimensional Koopman operator, and we want to, at some stage, truncate or discretize or approximate whatever to a finite linear matrix, okay, a matrix approximation, and then maybe compute spectral properties of that. So here's what can go wrong. So I'm taking what's called the bilateral shift on little L2Z. So if you're thinking of what this Hilbert space might be, it could represent the coefficients, the Fourier coefficients of a periodic function, periodic L2 function. And then what this a two-way infinite matrix does is just shifts the coefficients back by one, okay, the index. So you should think of this as sort of a two-way infinite Jordan block that's not really doing anything to the expansion of your functions other than changing the index. Um, when you view it like that, you should hopefully see that this operator preserves the norm of your vector, right? The energy. And in fact, more is true. It's unitary. So the spectrum in this case is the unit circle. The spectrum is stable, meaning if you add small perturbations to the operator, it doesn't change the spectrum too much. And you get continuous spectra. So there are actually no eigenvalues, right? There are no normalizable eigenfunctions, and you have unitary evolution. Then when you discretize or truncate to a finite matrix on the right, which is what you would do if you were doing EDMD in Koopman, for example, as we'll see later, you break all of the nice properties. You get a Jordan block, a finite Jordan block, which is the bad guy of numerical linear algebra. Okay, the spectrum is zero. It's exponentially unstable than the truncation size. It's discrete. It's also got complicated multiplicity properties. It's got nilpotent evolution. Everything breaks. And the problem is that, okay, this isn't just an academic example. Lots of Koopman operators experience the same phenomena. In fact, even for measure preserving systems, a lot of Koopman operators are built from shift operators that look like this. Right. Okay, so what I'm going to do is try and figure out how do you actually control this phenomena. Okay, so we can look at this and we can see that the problem associated with this truncation is that the subspace we're projecting onto is non-invariant, right? You've got a closure issue. And that's really underlying the theme of this talk. How do you control closure issues for Koopman operators? Okay, so here's sort of I think the most popular method people use, it's fair to say, for approximating spectral properties of Koopman operators, EDMD. So it goes back to Peter Schmidt, who studies dynamic mode decomposition, which was then connected to the Koopman operator in this paper here. And then it was really this 2015 paper, which is one of my all-time favorite Koopman papers, where they made the explicit connection with a Galerkin approximation. So what you do is you take a finite set of observables, psi1 up to psi n, and you build a approximation of the Koopman operator on the subspace corresponding to the span of these basis or dictionary elements. To do that, you need access to two types of inner products. The inner products between the basis functions themselves and with a Koopman operator K acting on the left here. Now remember, all we have access to are these snapshots. So what we do is we interpret these X points in our snapshots as quadrature points, and then we put quadrature weights. Okay, and we can approximate these inner products explicitly in terms of matrices over here. So this psi X is just the dictionary evaluated at the X points. And then if you want to apply the Koopman operator, this is very easy. It's just composition with F. Even though F is unknown, we still have these Y points, these sample points here. Okay, so you just trade this psi X for psi Y. Now, I'm not going to really discuss how you choose the quadrature weights. That depends on the dynamical system itself, how you collect the data. So one example would be if you have an ergodic system and you have a single trajectory, then under suitable conditions, you could set all of these weights to be 1 over capital M, and then you get convergence using some sort of ergodic theorem as well. But anyway, however we do this, we're going to end up with a Galerkin approximation, which is just the inverse of this matrix applied to this matrix. That's mathematically what's going on. There are numerically more stable ways to compute this, and really, Zlatko in the audience is the expert on sort of the finite dimensional numerical linear algebra tricks that you use to get good results there. But mathematically, this is what you're getting. Okay, so does it work? Uh, no, it doesn't. It doesn't approximate the spectral properties all the time. So it converges in a suitable sense called the strong operator topology, meaning that if you act on a specific observable, then you converge as you collect more data, and then you increase the dictionary size. But if you want to get spectra, it doesn't typically converge. So here's an example. This is the Duffing oscillator. Okay, with this alpha parameter that controls the dissipation, and this is sampled at a discrete time step over here just to get a discrete time dynamical system. And the way I'm going to apply EDMD is with Gaussian radial basis functions. So this is actually the choice that was in the original EDMD paper. And then I'm going to randomly sample, okay, my snapshots. So that's Monte Carlo numerical integration to get approximation of the inner products. And I've set the number of snapshots very large so that they don't really affect the results. Over here, I've set alpha to be 0, so this is no dissipation. The system is Hamiltonian. And in fact, in this case, the spectrum is the whole unit circle. These blue dots are the EDMD eigenvalues. You see that you get a lot of spurious stuff. And this is exactly the same phenomena is here. This is due not to any sort of weird numerical artifact. It's purely, well, it's a mixture of that, but also the main driver is the truncation from infinite dimensions to a finite dimensional subspace. So even if you had perfect measurements, infinite data, no errors, you'd still get this phenomenon. The contours here, the epsilon contours, correspond to that approximate point pseudospectra. I'll show you how to compute that in a bit. Here I've switched on the dissipation. It's a little bit less clear what the spectrum is in this case, at least on L2 spaces of observables, but you still get the same phenomena. You can still get these spurious eigenvalues, and you can track the error of the eigenpairs as you increase the matrix size, so that's the number of basis functions, and it doesn't
Matt,
compare. Yes.
would it be would it be right to say here that actually EDMD cannot converge in that sense because the limit would be compact, and the Koopman is compact only in
Ah,
a
so,
in a non-atomic case, which is like a
so you can have uh, strong operator convergence of operators, which preserves good spectral properties without it being compact. So a good example would be you take finite element approximations of elliptic self-adjoint operators.
Hmm.
Okay, and then you've got a discrete set of eigenvalues, and the spectrum will converge, and that's definitely not compact. But what you typically get in practice, and in fact there are theorems that characterize this, is that this pollution effect occurs whenever you have essential spectra. And that's connected to whether you have a compact resolvent, and so compactness does come into play, but it's not a deciding feature. But yeah, that's a great point.
Maybe I can comment a little bit. I don't know if Alex is here as well, so he could comment on this. But Zlatko, it's also the consequence of working in L2, where
Yeah.
this particular system has, the full unit disk as the spectrum, and so that's why you're seeing all this inside stuff. If you successfully worked in these, for example, modified Fox spaces or things like that, then it's quasi-compact and it would actually have a point spectrum. So you could get it by adjusting the kernel, quote unquote.
Yeah.
Okay.
Yeah. So spurious or spectral pollution is very much tied to the space that you're working in. Okay. So how do we fix this? So this is sort of, I guess it's an old algorithm now, at least in Koopman terms, a few years old. So we look at the Galerkin approximation, and we look at the color scheme, and then we think about, okay, we've got this matrix G, which is the ground matrix, this matrix A, which represents the action of the Koopman operator. We can take its adjoint. What's the missing matrix, or what's the missing correlation? And it's this green-green matrix, right? And that really allows you to control closure issues. So for example, suppose I have an observable inside that's represented uh, as a linear sum of these dictionary elements. Then I can take this residual squared. So remember, this is the epsilon squared corresponding to that coherency parameter we were looking at. This is this inner product. I can expand out here. And then assuming my quadrature rule converges, this is a large data limit of this thing here. So notice two things. First of all, there's a nonlinear dependence on the spectral parameter, but also these matrices L, A, and G are finite. Okay, so I can always track the error when I sort of hop out of my subspace when I apply K, okay, with these finite matrix approximations. Okay, that's really sort of the idea of this talk. If you forget everything that I've told you, think of green. Okay, so we can turn that into an algorithm for computing approximate point pseudospectra. I'm not going to go into the details of that yet because I'll show you it explicitly for reproducing kernel Hilbert spaces later. But this allows you to get these contours, and then you can play games with sort of adaptively shrinking this epsilon to get a conversion algorithm to the spectrum. And this figure, by the way, is in a preprint with Igor that I'll reference a bit later as well. So if you want the experimental details, go into that paper. Okay, so that's sort of I guess sort of like an intro into spectral properties of Koopman operators, but we can sort of step back and think a bit more about this result. So we can start to attach theorems to these algorithms. So I'm going to sort of state this in a general term without being too precise. If you want precision, then you can find this paper on my website. So I'm going to consider the space of observables with finite energy, okay, this L2 space. And then the theorem says there exists algorithms, gamma, n, and m, using these snapshots that converge to the approximate point pseudospectrum for all systems. Now, of course, I have to have some assumptions like f being continuous and the a non-singular with respect to the measure and things like that. But for the sake of this talk, you can just think of it as a generic system. And this looks great, right? We can, pack up, we can go home, and we've got an algorithm that seems to, work in practice, but also in theory as well. And then we actually look at this again, and we think, okay, well, I've got a double limit, right? M going to infinity, then n going to infinity. And I don't think anyone in the audience has ever gone to infinity. It's a very expensive process. So really, you want to do better, right? Can you beat this double limit? Can you, for example, choose the data size depending on n or vice versa? Sometimes you can, but actually sometimes you can't. So this is where sort of we get into classification, which is really what this paper down here is all about. Okay, so for DMD methods, we always have these two parameters: n, the size of the dictionary or basis; m, the amount of data, which you can think of as quadrature. And it turns out that for some problems, you can't avoid having to take a double limit. So here's an example theorem. So here we're getting an impossibility result by constructing an adversarial class of dynamical systems. And I'll walk you through the proof. So what I'm going to do is consider dynamical systems on the closed unit disk in R2, such that F is continuous, measure preserving, and also invertible. I can even make it smooth if I want. And this implies that the Koopman operator is unitary. So it's a very nice, well-behaved operator. I'm not assuming it has discrete or continuous spectra, which actually is one of the mechanisms behind this result, but that's another story. But I'm fixing this class. And then I'm going to allow my algorithms to do a lot. So I'm going to have very strong algorithms. They're allowed to do very strong things, which will improve my impossibility results. So the stronger assumptions I have for my algorithms, the more shocking or the stronger it is when I have an impossibility result. So I'm going to assume my algorithm can sample F, so it can collect these snapshots at any point inside the disk, the state space, to any accuracy that it wants. Okay, so it's free to choose the accuracy. So you can think of this as a perfect measurement device. So you're free to choose as many points as you want to as high accuracy as you want as well. And then the result is the following. So there does not exist any sequence of deterministic algorithms, gamma n, using this perfect measurement device that converges, as you take n to infinity, to the approximate point pseudospectrum for all f in this class of dynamical systems. So a few things before I show you the proof. N, the little n here, it's just an index for a sequence of algorithms. It can index anything. It's not tied to a dictionary size or the amount of data. It can be anything you want, right? It could be the size of a neural network, whatever. So this is a universal result, and it also applies to any type of algorithm or computational model. So even if you were allowed real number arithmetic, the result would still be true. And what we actually prove in the paper is a slightly stronger result that you can't even do it with random algorithms with probability greater than 1/2. So even if your algorithms can randomly sample within the disk, or if they're allowed to do things like stochastic gradient descent, whatever, it's still impossible to do better than random coin flipping. Okay, so let me talk you through the proof, and then hopefully the mysterious sort of property of this small n will become a bit clearer. So how does the proof work? We're going to base the result on a phase transition lemma. And this is one of the things that when So when I was writing the paper with Igor and Alexei Stepanenko, who was a postdoc on mine at the time, it was really fun to sort of get into the dynamics, right, that were driving each of the impossibility results we were looking at. So you always need sort of a lemma that sort of captures some sort of phase transition. So let me explain what I mean by that. So I'm going to take rotation by pi on the disk. Okay, you can use Dirichlet eigenfunctions of the Laplacian to show that the spectrum of the Koopman operator there is plus or minus 1. Okay, and then there's this result that says that if you have two distinct points inside a set of points x and y inside an annulus in the disk, there exists a measure preserving homeomorphism H that acts as the identity of the annulus, but so that if you take h of x, rotate by pi, you get h of y. So if you imagine taking the inverse of h over here to the right-hand side, what you've essentially got is conjugacy of dynamical systems, at least on the data. So you're looking at the map x to y. It's conjugacy with f naught. And the idea will be to use this impossibility result to trick an algorithm into a sequence of algorithms into not converging. So let's do that. So it's a very general result. We don't know anything about the sequence of algorithms, so there's really only one way you can start the proof. So suppose for a contradiction, there exists a sequence of algorithms that always converge in a single limit to the spectrum. So now we're going to build an adversarial F. We're going to start off with a slightly perturbed rotation by pi. So here it is in polar coordinates. I'm adding a bump function here. And you can use Weyl sequences, so those are approximate function sequences, to show that the spectrum of the associated Koopman operator is the whole unit circle. So if you pause for a second and think, what I've done is I've perturbed my rotation by an arbitrarily small amount, and suddenly the spectrum's gone from plus or minus 1 to the whole circle, right? The spectrum is a very brittle object, even for measure-preserving invertible systems, even for smooth measure-preserving invertible systems. Okay, so how do we use this? Well, this F1 tilde, we assumed this sequence of algorithms converges for all F. So it certainly converges for F1 tilde. So there exists some N1 so that I is at most 1 away from the output. Okay, and this is because we assume convergence to the spectrum, and the spectrum is the unit circle. Now, when gamma N1 is given the dynamical system, it can only use a finite sort of number of queries to this oracle, or this sort of, you can think of it as this perfect measurement device, right? So I'm going to let x and y correspond to those snapshots that it's seen. This allows me to construct an F1, which is conjugate to this rotation by pi, okay, by H1, this homeomorphism that we know exists from this phase transition lemma. Okay, so if I'm losing you, don't worry, there'll be a picture in a slide's time. So I've got this conjugacy, and remember, the lemma is such that the data is consistent, which means when the algorithm samples the dynamical system, it's given the same data, okay? And it's a deterministic algorithm, so it has to behave in the same way, both of these dynamical systems. In particular, this this inequality here has to hold also by replacing, when I replace F1 tilde by F1. Okay, now you can start to see the problem. The spectrum of this F1 is the same as the spectrum of the rotation by pi, because this H1 only induces a unitary change of the Koopman operator, and I get plus or minus 1. So I'm flipping between these two pictures here, okay, by sort of changing the dynamical system whilst preserving the snapshots. And what I do is I do this on a cascade of annuli that shrink to 0. Okay, and because I'm the identity of each of these annuli, I'm doing this in a consistent way, and I can take a limit, okay, for different nk. This limit, this f, lives inside my class of dynamical systems. It always satisfies this inequality here, but f is conjugate to f naught, so its spectrum is plus or minus 1, and this contradicts convergence to the spectrum because I is certainly, complex number I is certainly more than 1 distance away from plus or minus 1. Okay, so this is sort of the picture. You're assuming a sequence exists, and then you're doing a sequence of sort of phase transitions along a cascade of annuli to show that you can't compute in a single limit. Okay, so that's sort of the overview of the proof method. Um, if I went too fast, apologies. But what this allows you to do really is sort of step back and start to think about classification of dynamical systems and computational problems. And here we're going to use something called the solvability complexity index. So this is the fewest number of limits that you need to solve a computational problem. Okay, so delta 1, so these will always be sets of computational problems, or you can think of them as classes of dynamical systems. So these will be problems where I can solve the problem in one limit, but I have full error control. Okay, so I approximate the spectrum of the Koopman operator with a sequence gamma n, and the error is always controlled by 2 to the minus n. The exact rate here doesn't matter because you can always reparameterize n. Just think of it as a known convergence. So SCI, the fewest number of limits needed to compute something. Delta m plus 1 will be problems where the SCI is at most m. So there's sort of a unfortunate mismatch between m plus 1 and m here. That's to align with classical hierarchies. I won't go into that. But if I go back to this result here, this is saying I can't do it in a single limit, so I do not live in delta 2. This is saying I can do it in 2 limits, so I do live in delta 3. Okay, so I have a precise classification of where I sit inside this hierarchy by proving convergence of algorithms, so upper bounds on difficulty, and impossibility results through lower bounds on difficulty through adversarial dynamical systems. You can also do things like error control, so final limit from below. So this means that you, for example, sigma 1, you converge in a single limit. You don't have full error control over the whole spectrum, but you know that for any finite n, there's a control on how close your points are to the spectrum. And you have this sort of dual notion where you swap the role of the spectrum and the approximation. Okay, so verification. So up here, you can trust the output. Down here, you cover the spectrum. And this really leads to trustworthy Koopmanism. Okay, so this looks like a crazy idea until you actually start to go into the literature on Koopman methods. So this is a very incomplete table, just to give you a flavor of an idea. But here are some algorithms that approximate different properties of spectral operators. Here are some of the assumptions. And here are the things that these algorithms might compute. So the Koopman modes decomposition, the spectrum, if it's measure preserving, the spectral measure, the spectral type, so is it eigenvalues or continuous spectra. And if you go into all of these methods, when they're proving convergence results, they're always proving upper bounds on the number of limits that you need to take to compute something. So an upper bound on the SCI. So one of my favorite is resolvent compactification. It's a beautiful paper, and they prove that you could compute certain things in 5 successive limits, right? So you need to take 5 parameters to infinity for this algorithm to compute something. It's a similar story if you do things like Ullm's method for Markov processes or methods that compute SLB methods measures based on smoothing and stuff like that. You also get a similar picture in control as well. So really, the literature on Koopman operators so far has only proved upper bounds, right? And the natural question is whether these are sharp. Can we lower the number of limits or take parameters that, control one parameter in terms of another to avoid this expensive process of having to go to infinity lots of times? Okay, so in the paper, we started this classification program for various types of Koopman operators and also problems. So we looked at computing the spectra, but also spectral type and measures and things like that. But here's the picture for computing the spectrum. And here are 3 different classes of dynamical systems. So if I take the most general class where f is just continuous, you can show that it lives up here, pi 3, so that's needing 3 limits with the final limit from above. So you're shrinking to the spectrum. And you can prove this is sharp. You can't do better than 3 limits. If you assume that it's measure preserving, you hop down here. So you need 2 limits. And you can't do it in 1 limit. So those were the results the impossibility result I showed you earlier. You can also assume that you have control on how regular f is, so modulus of continuity. Okay, so this is telling you how much quadrature you need, how many data samples you need to get those inner products. If you do that, you live here. So you have two limits. And what's really cool about this hierarchy is that it comes with a calculus. So I can take the intersection of these two classes, and I know immediately that it lies down here, sigma 1. So that's convergent in a single limit with verification, with error bounds on my computed approximation of spectra. Okay, so if I know my system is measure preserving, and I also know a bound on the modulus of continuity, then I could get an algorithm which converges in a single limit with error control. Okay, so this allows you to sort of build optimal algorithms and classifications of dynamical systems, and this is really only the this paper is really only the start of this process. Okay, so we've got this sort of negative result that we need two limits for measure preserving systems. So what I'm going to do now, so we know that negative result is true, right? You can't beat it. It's a theorem. There's no way around it. But we can change the question, and this is really sort of a trick that lots of great mathematicians do. So I quite like this quote here. Apologies if you're French and I'm offending you, but mathematicians are like Frenchmen. So whatever you say to them, they translate into their own language, and forthwith it's something entirely different. Okay, so someone working in fluids might say, okay, I want to study the Koopman operator, and you can say, aha, which space are you working on? Which space of observables? So let's perform this trick by changing the space, and let's see whether the classification becomes easier or harder. So a reproducing kernel Hilbert space, what is this? So this is just a Hilbert space of observables or functions on the state space, so that for each state in the state space, the linear map that takes an observable g to g of x, this is a bounded linear functional. So if you're struggling to think of an example, think of a Sobolev space. So when you do Sobolev embedding theorems for sufficient regularity, that's telling you that this map is bounded. Okay, and then once you have this structure, this condition rather, you know that there's something called a reproducing kernel, which is a map from X across X to C, which gives you the Hilbert space structure. Okay, so Riesz representation theorem says that as soon as this is bounded, there's a vector living inside your Hilbert space, Kx, which gives you evaluation at X through inner products. And then this kernel is just this inner product here. Okay, so don't worry so much about the details of this. What's important is that I can evaluate inner products, which are sort of the building blocks of EDMD methods, using kernels. Okay, and this is much cheaper than quadrature and using data. So some quick advantages of changing the space. If you generate forecast bounds, you immediately get pointwise error bounds instead of just L2 bounds. They actually can be used as a way to make high-dimensional systems practical. There are often fast methods for evaluating the kernels. And different Koopman operators lead to different kernels lead to different Koopman operators. So you can tailor them to the application. And this is something that, of course, Igor and Alex know a lot about. And this is one of the directions that the Koopman community is heading at the moment, is sort of how do you change the function space to capture different interesting properties. But we'll see in this talk that it leads to fundamental possibility gains. So by that I mean, if I go back to that crazy hierarchy, it lowers the difficulty typically. So how does this work? Well, there's a beautiful duality. And this is really this paper here, which is a preprint with Nicola Boulay at Imperial and our student Gustav Conradi. So it was really Gustav who spotted this duality, that if you take the adjoint of the Koopman operator and you act on this kernel function, that's the same as taking the kernel function and f acting on your original state. So you're now looking at the evolution of functionals. And there are also ways to get Koopman mode decomposition and forecasts as well. But let's just focus on K star. So why is this nice? This means that if I want to approximate the action of the Koopman operator on these functions, so I'm thinking of these as my dictionary elements, I replace this x by f of x, so I replace blue by green. So I can get these three matrices I had before that I was using in ResDMD, by just evaluating the kernel at the snapshots. And this allows me to get this residual without a large data limit. So remember, before we had to take m to infinity to get this residual. Now we don't. So this allows you to build algorithms, for example, for approximating the approximate point pseudospectrum. So here what I'm doing is I'm taking this residual, this exact residual, no quadrature approximation, and for each set of points lambda over some grid, I'm finding vectors g that minimize this residual, which boils down to a generalized SVD or eigenvalue problem. Okay, this gives me a set of these pseudo eigenfunctions, and I can even prove that the set of spectral points will be a subset of this approximate points pseudo spectrum. And as I take n, the number of snapshots or the size of my dictionary to infinity, I'll converge. So for very broad classes of dynamical systems, I can get past that two-limit barrier we saw before for the L2 case. So theoretically, it's very useful, but also practically, it's very useful as well. So this is where I want to sort of give you an example of doing spectral approximations carefully for Koopman, leading to state-of-the-art results. And this is the paper with Igor and Alexei. So the problem we looked at was uh, predicting sea ice concentration in the Arctic. So you have a grid of points, okay, over the Arctic region, and then you collect satellite data, okay, from the last 40 years, and then you try and predict the sea ice concentration over the grid points in the future. And this is very hard to do. It's very hard to find which regions are geographically important. It's also very hard to predict more than 2 months in advance. So this is a well-known problem. It's a very chaotic, noisy, nonlinear system. Okay, so what I'm going to do is I'm going to choose a reproducing kernel Hilbert space that's built from a poly-Gaussian kernel, and I'm going to combine that with delay embedding. And what I do is I get spectra that look like this. So these are the eigenvalues. These are sort of the finite truncation eigenvalues, or EDMD eigenvalues. And I can color each of these according to the residual to check whether they're spurious or not. Okay, so how accurate do they represent the infinite dimensional Koopman operator, right? So you always have this closure issue. So that's what the color is. And you have okay, so you have a few interesting modes here. So you have the mean sea ice mode, okay, it's sort of just the average. And then you have the annual sea ice variation. So it's monthly data, so it's period 12. So these modes correspond to ice melting and ice then reforming in winter. And then you also, amongst a lot of these spurious guys, you get these interesting decaying modes, okay, which you can track here. So these are the Koopman modes. So these give you sort of the physical regions where you're seeing the excitation of this type of behavior. Okay, we were really excited when we saw this because these types of decaying modes have been detected in the Antarctic before. So Igor has a very nice paper on that, but it was very difficult to get them in the Arctic, right? Because of the nonlinearity, and you can see why, because of this sort of sea of spurious stuff here. How do you extract that without the residual? Okay, so this is a nice picture, but can we actually take it to the next level and use these to forecast sea ice? And that's what we did. So we solved a binary accuracy problem. So that's determining whether a grid point is covered in ice or not. So there's a standard 15% threshold that people use in the community. And then we looked at the accuracy of that binary classification problem in terms of lead time. So lead time is the forecast time. So in yellow, you see our results. In blue, you see a previous state-of-the-art neural network-based method. In red, you see a previous sort of classical dynamical systems model. And here what we're really doing is we're using this residual, this epsilon, to filter out the spurious eigenvalues and get a good reduced order model. So remember, the smaller you can make epsilon, the longer time period you have a good coherent structure. Okay, so this is what we're doing to get this result. Okay, so that's
Matt, if I may,
Igor.
I'd also like to point out, and I think this is quite important, that we're using way less. This is all on the CPU, correct?
Oh yeah. So this is in like a fraction of a second on my old rubbish computer with like
I'll buy everybody a t-shirt and say no GPUs.
Exactly. I've got a paper that's not a paper, sorry, a t-shirt that says "Hit it with Koopman." So I should maybe put on the back of it, "No GPUs needed," something
Yeah.
like that. Yeah. So it's much more efficient than training for on GPUs for several days and then.
There is a beautiful correlation here because at the same time, saving CIs and it means using
Exactly. Exactly.
less GPUs.
Yeah. Okay. So that's a use of these residual ideas. We can also classify the spectral problems based on the space that we're working in. So here I've summarized those L2 results I flashed up before. So you have general systems over here, measure preserving, modulus continuity combine. So this is for epsilon equals 0. So that's the spectrum, not the pseudo spectrum. You can do the same thing with reproducing kernel Hilbert spaces. So notice in particular that you shift to the left. So the problem becomes typically easier. And then you can ask the question, if I don't get the spectrum, but the pseudo spectrum, if I allow epsilon to be non-zero, does it change? And then you can, oops, sorry, you get this horribly complicated looking diagram. But the point is that you can precisely classify them. And the difficulty depends on the problem. So epsilon greater than 0 becomes easier, and also the space. Okay. So what about forecast bounds and dictionary learning? So for the last 5 minutes or so, I want to sort of tease you a little bit with a paper that we've just put up on the archive. So in this paper, what we're doing is we're taking these ideas and we're using them to not just compute spectra, but tell you how sort of give you an upper bound on the forecast error. So one way you can do this is through something which we call principal angle decomposition. So this is essentially measuring the principal angles, so that's the vectors and how they change between V, your initial dictionary, and K of V. Okay? So you're looking at the invariance in a geometric way, and this is sort of a classical built on a classical method that you see in CCA and image analysis as well. But really, to make this work for Koopman operators, what you need to do is have this extra L matrix. Remember, that's the green matrix. Okay, and that allows you to control the closure. So here's an example for the Duffing. I guess maybe it shouldn't be called a tractor, but Duffing oscillator. Uh, Here are the principal angles. Okay, and you can see the error here. And what you can do is rather than truncating according to a singular value decomposition, which is what we typically do in POD and DMD and things like that, you can truncate the SVD component of this algorithm according to the invariance. Okay, and this gives you a very nice, fast, non-iterative method that gives you immediately the best sort of compression rate in terms of invariance for your dictionary. Okay, so here I have one-step predictions, the number of modes that I keep in my dictionary, and I'm comparing the SVD, which is sort of the standard method people use, to PAD, this principal angle decomposition. Again, you can see that, of course, for large time steps, everything sort of saturates, but for initial time steps as well, you really see a big difference. And it's a similar story for the Lorenz attractor. So you can start to use these residuals in this way. You can also use them to get error bounds on forecasts. So here's an example of from the paper where we're applying it to the system of Pluto and its moons, or satellites, I should say. I'm not sure all five of them are moons. I don't think Pluto's even a planet anymore. But anyway, so you have Pluto and then the big five objects orbiting Pluto. And you get this very complicated sort of two-body system with these other perturbations. It's a complex system. Okay, and what I'm going to do is use error bounds that we develop for multi-step predictions that apply both in the L2 and RKHS settings as well. And I'm going to look at how they perform. So here I'm using the Koopman mode decomposition to predict the position of one of the satellites. I can't remember which. So here you have the actual error in terms of the prediction in days. Here you have the bound, the rigorous bound that we prove gives you an upper bound. So it's good that it's above the true error, but it's also pretty pessimistic. And we do this with an RKHS kernel using RKHS space using a Matern kernel. But what you can do as well is you can study this in a statistical sense. So not just look at the worst case error bound as you leave the subspace, as you move beyond your dictionary, but in an averaged sense. So you can study Gaussian processes, which are meant to sort of measure in an average sense how much leakage is there when you move from the finite dimensional subspace you're working in to future applications of the Koopman operator. Okay, so this is just sort of a very rough idea here, but you can see that then you get really good, typically, um, approximations of the error, right? So particularly for chaotic systems where there are some interesting statistics behind these processes, you can capture them, you can learn them from data and really nail the prediction accuracy. And once you've got a diagnostic like this, you can start to use it as part of a routine to train a dictionary. Okay, so not just start off with the dictionary you started with, or the PAD, the principal decomposition, but to actually train, for example, the kernel or maybe a neural network that's giving you a dictionary. Okay, so this is what we did for this system. Okay, and you get much better, much smaller, I should say, errors, right? And you're able to track this here. So here we were just doing it with stochastic gradient descent. Okay, and that allows you to start off with a kernel. You then train the kernel and you get an optimal, um, or a better rather, kernel for your particular system. One of the nice things about this, I should say, is that if we go back to these kinds of algorithms, you don't need any additional data to get this matrix, right? So you don't need to split up uh, the the data that you're using for training into, one set to maybe get a good to build a model and then another set to test it. You can do everything in one shot. Okay, so it's very useful in terms of being more efficient for the data that you have. Okay, so. I'm running out of time, so let me just end with two very quick shameless plugs. The first of which is that there'll be a book appearing in August this year, which looks at infinite dimensional spectral problems. Okay, and in particular of interest to this community, I think, is the final chapter, which is also the longest chapter, right? So this is one of the chapters I really wanted to focus on. And in this talk, I've sort of given you a flavor of some of the problems that are studied here. And this gives you sort of a systematic, rigorous, but practical way to compute spectral properties of Koopman operators. So there's hundreds of classifications in this hierarchy, algorithms, examples with full code and exercises as well. So if you also see anything else that interests you in this list, for Koopman or otherwise, please do get in contact. I'd love to chat with you. And then second shameless plug is we'll be having an Isaac Newton Institute program in August this summer for the whole month on Koopman operators and other operators in dynamical systems and how spectral theory and machine learning and things like that interact in these domains. So if you're interested, then please do get in contact. So this is the Isaac Newton Institute. As well as the science, Cambridge is also a beautiful place to visit. I think, well, many of you in the audience have visited me here, Igor as well. I think we have some fond memories of the Wren Library and Newton. But if you want to come and sort of hang out, then do get in touch. We'd love to have you here. Okay, so pointers. Data-driven spectral problems for Koopman operators are hugely popular, but standard truncation methods can often fail. So we saw this for EDMD. So really, to do this properly, you need to understand how the infinite dimensional aspects of the Koopman operator interact with your finite dimensional approximations. So I've hinted at some general methods with convergence guarantees. So in fact, we have algorithms for spectra, pseudospectra, spectral measures, and so on. You can find all of these in this book. And I gave you an example of verification of these eigenfunctions for practical gains for sea ice forecasting. There's also a hierarchy that allows you to figure out how difficult these problems are through adversarial dynamical systems for impossibility results, and also these sort of new infinite dimensional flavored algorithms. So it's fair to say that at least on L2 spaces and RKHS spaces, we now have a pretty near complete picture for spectral properties. So certainly not the case for things like control and stuff like that, but at least for approximating spectra. So really, the next step in this technology is sort of translating it into those other domains. And then finally, I showed you how this matrix L, this green-green matrix, leads to forecast bounds, ways to train dictionary in this new PAD method that can often be more efficient and accurate than the SVD, at least for capturing dynamics. I think that's a good place to stop. Thanks a lot for your um, well, yeah, for your questions and also paying attention.
Thank you, Matthew. Um, Now we have a few minutes for a question. There was some question in the middle as well, but let's open the floor for more questions. I have a quick question for you, Matt,
Yeah.
since I get so do you see for Henkel DMD? Not do you see spurious? I can like can you say an
Yes. Yeah. So, for example, let's go back to this drawn block picture.
okay.
Let's suppose that, and in fact, you can do this with something as simple maps on tori and Fourier coefficients as your dictionary in an EDMD method. If your Koopman operator has what's called Lebesgue spectrum, then if you do Hankel DMD, you're doing a Krylov approximation, and if you took an infinite number of delays, your Koopman matrix would look exactly like this, up to some reordering or whatever. So that means that when you truncate, you're going to get exactly the same phenomenon. And I think Igor has a very nice example of this. Is it the doubling map, Igor, in one of your papers? And you get essentially the same thing when you're doing Hankel DMD. So Hankel DMD, what it's doing essentially is EDMD, but with the dictionary chosen according to a Krylov subspace.
Right.
So the
So
convergence results for Hankel DMD will apply when you have a finite dimensional invariant subspace inside your dictionary. But of course, when you don't have that, that breaks, and that's what you're seeing here. This closure issue is really the problem.
For
so
periodic and quasi-periodic attractors, you're going to get either a finite dimensional subspace or something very, very close to it, so
Yeah,
you can prove things. But if you have something like a cat map,
exactly. Yeah. So exactly. Yeah.
that's
Yeah.
the example I originally gave that had
Yeah.
this kind of a structure. So for chaotic systems, it's way more delicate, as Matt pointed out.
Yeah.
I guess we could combine Res DMD with Henkel.
Oh yeah.
Yeah. No, just
That's one of the
yeah.
yeah. I mean, that's one of the examples I use in papers. So for example, I mean, I've not given you the residuals here, but here I'm doing some sort of delay embedding, essentially Hankel DMD with some bells and whistles, and
Mhm.
yeah, you get spurious eigenvalues, but you can still use methods to get the spectral information using the same information. An
Great. Thank
interesting phenomenon actually is that um it's not always as bad as the Jordan block. So the Jordan block here is oh sorry, I've gone too far. Although the spectrum is zero, the spectrum is unstable. So when you're dealing with noise, typically the spectrum sort of shatters and goes to the boundaries of the pseudospectra, which collapse to the unit circle as you increase n. So there are some complicated effects there as well, but yeah.
Great. Thanks.
And
Uh,
I'll just say thank you very much, Matt. I have to leave for another meeting, but
Yeah,
thank you. See you soon.
okay.
see you soon.
We're at the top of the hour. So any last minute questions for Matt before we end the seminar? Great. So our next seminar will be in May, towards the end of May, and I will send out an email to put that on your calendar. So thank you very much, everyone. We'll see you next month.
Thank you. Yeah, looking forward to it.
Bye.
Bye bye.